Hi sir, we are class 2 from Calculus 3 subject majoring in Industrial Engineering batch 2022. We are going to explain about partial and directional derivative. This group consists of me Azzam and my friend Kevin. So this is our full name and student ID. My full name is Abdullah Antariksa and my friend Putra Asmin Kevin Aditama.
Okay, my name is Putra Asmin Aditama and I will explain about partial derivative. The partial derivative of a function of several variables is a derivative with respect to one variable, with the other held constant. It measures how to the function changes as one variable changes, while the other variables are held constant.
Iya nggak jelas.
First thing I want to do is want to grab a function, so gonna grab f. So it's multivariable function. So it is f of x comma y. So this is actually gonna be a surface equal. I'm gonna scale this thing, so I just hit divided by it. So it's gonna be x squared times y, and then I'm going to divide it by 25. Just to kind of like make things a little smaller, and then I'm gonna subtract it. So what I want to do first, I want to look at partial x. So you can look at partial x. I need to hold y constant. So to hold y constant, what I'm actually gonna do is I'm gonna make a slider. So I'm gonna call it yc from the y coordinate, and I can drag this, but nothing will happen because I let it was create a slider. Now what I'm gonna do? What I'm gonna do is I'm going to create the vertical plane y equal yc, and I'm gonna grab that end so you can see it pops upright and away, and if you go to your slider and move it, you can see it. You can see it past the surface, and that's going to be k. So that's what it's mean. We hold y constant, we're just gonna live inside the plane. So what's going to happen we are gonna look at the intersection of this plane and with the surface. So I'm kind of dragging it around. You can see it little bit. So let's try figure that out. That's also we are finding partial x, which means that we are gonna hold y constant, take the derivative with respect to x and see what's happened. So I need to find the intersection. So the intersection of this plane, which is y equal yc, with the surface is actually the trace of the surface in the plane. And so what I'm going to do is I'm gonna make a curve to find I'm gonna use curve to find that. So it's curve, and then x is allowed vary. So I'm gonna make that my parameter. So t comma y is not allowed to vary. It has to be whatever y sub or yc is. So yc comma, and now to get the trace I can do something kind of clever. So I'm gonna f of, so x is from this curve, x is just equal to t, and then y is being held constant as yc, and then so out of the parenthesis comma t is my parameter, and I'm gonna go negative 100 to 100 just because that's I'm guaranteed to see it. Don't press enter. You can see as soon as I tap it kind of filed itself in, and if we go back to our slider and move around it,
So for directional derivative will be explained by me. The idea of a directional derivative is that when we are looking at an xy plane and we have a function such as f of xy equal to x squared plus y squared that takes in two variables and spit out an output, we want to think about the way that function changes. The first thing that we learn is to use partial derivative. For example, the partial derivative with respect to x in this case give us 2x, and the partial derivative with respect to y give us 2y. When we do, for example, the partial derivative with respect to x, we say all variables that aren't x are a constant. And then we differentiate this function just like any other function. That essentially means that in our xy plane, we are looking at variables other than x, such as y being a constant, and just looking at how the function changes as we move in the x direction. Similarly, the partial with respect to y talks about just changes when we move in the y direction. Now the question is, what if we want to move in the direction of some other unit vector u with coordinates x naught and y naught? In that case, we are looking at what called a directional derivative. So directional derivative is a derivative in a particular direction in our xy plane. To compute directional derivative, we can simply use this notation. So the directional derivative with respect to u out of the function f at the point x naught, y naught equal to just a simple dot product, the dot product of the gradient and the direction of the vector. So in this example, we are going to talk about a function. It's 2 minus x squared minus y squared. And I'm going to investigate this at the particular plane 1 over 2 and minus 1 over 2. That's my x naught and y naught. And then I'm going to go in the direction. My u direction is going to be the direction 1 over root 2, 1 over root 2. The partial derivative of this function I can do, and thus I can make gradient vector to be the derivative of the first component. That's the minus 2x partial respect to x. And then the second components part are in respect to y is the minus 2y. And then I evaluate at my given point and I do it with the direction of the vector. So the next thing I can do is I can actually plug in my point and I'm going to get minus 1, 1 for my gradient and evaluate this point. Dotted with the 1 over root 2, 1 over root 2 and the result is 0. So this is GeoGebra application. Here we are going to see the 3D model from the previous example. So from the previous example, the function is 2 minus x squared minus y squared. And this is the model. As we can see, the top of the curve is the surface or the range, and then the low part of the curve is the domain of z or the interval such that function will be defined. And then I will also gonna show you the other model from the directional derivative. This one, this one, this one, and this one. So this is the model. As you can see here, the intersection of the tangent and the direction vector plane shows the directional derivative.